Hi Calculus 1 students. Before going any further, this video is intended to my section 18. That being said, section 19, you're more than welcome to watch this video because in reality what I'm doing is I'm doing an example that section 19 did in class, but here it's much more cleaned up, okay? Because I'm presenting the theorem first and then I'm showing you how to solve this example using this theorem, okay? So for section 18, it's mandatory because we're not covering this example in class. So let's start. So the point of this video is to present you that theorem right here, the change of variable theorem when we are evaluating limits. And it happens when you have a function inside of a function. You know that g of f of x, like that you have seen before. And what it is quite simple. It's that we can kind of split the thinking process in two. Okay, so if f of x is approaching b from above as x is approaching a, meaning that the limit of f of x as x is approaching a is b from above, let's say. The reason why the b from above is important is because that limit is an intermediate step. Okay, so sometimes the fact that it's approaching b from above or from below will change the final result. So that's why you need to be careful. So if f of x is approaching b from above as x is approaching a, then the limit of the composite function as x is approaching a will be the same as just the limit of the outside function as u is approaching b from above. So in other words, we're replacing the function f of x by a variable u. Of course, the theorem has its counterpart when f is approaching b from below, right? So it's basically the exact same thing, except that u will approach b from below instead of approaching b from above. And question is, how is that useful? It's useful to solve this example. So the limit as x is approaching infinity of e to the power of x minus x squared. The first thing to realize is that if you directly substitute, the problem is going to be inside the exponent. Okay, so you'll have b to the power of infinity minus infinity. And I remind you that infinity minus infinity is a problem. It's an indeterminate form. You don't know the outcome until you perform a little bit more algebra. So, but what makes this problem different than the other ones is that this indeterminate form is inside the exponent. Okay, so, and that's why you want to use this theorem. So it's inside the exponent. So what do we do? Okay, so the first step will be to define a variable to be the inside of the exponent. So we're going to say, let u be equal to x minus x squared. And what we want to do is to compute the limit of u as x is approaching infinity. So then, and actually I'm going to do this underneath just because I want to make sure that I will have space. So then the limit as x is approaching infinity of u, and then you have to calculate this, right? So you're taking the limit as x is approaching infinity of x minus x squared. And now you already know that you have infinity minus infinity. Okay, so no point trying to directly substitute at that point. But remember the technique. The technique is to factor what's large. So factor what's large. Okay. And as you do this, so obviously this is an easy limit. So as you do this, you're going to factor, as you can see, the x squared. So x squared. And you're going to get, as a result, inside the bracket, 1 over x minus 1. And from there, direct substitution, noting that this little 1 over x will approach 0, will give you, so infinity times negative 1. okay, which is negative infinity. So I have a little bit of space to write that. Hopefully you see it's a negative infinity. Maybe I should just do this. Okay. So what does it mean? It means that so as as x is approaching infinity, u is approaching negative infinity. So the second step is now to change the variable, to apply this theorem. So in other words, look carefully, the limit as x is approaching infinity of e to the power of, and which color am I going to use here? I'm going to use orange, I think. Yeah, orange is easy enough to distinguish. So, of x minus x squared, okay? So this limit, and now we're going to change the variable. We're going to call this our u, and we know that u is approaching negative infinity. So it will be the limit as u is approaching negative infinity of e to the power of u. Okay? And now this limit is very easy to do. So it will give 0. So just as a quick recap of why this limit gives 0, and this is the final answer. It's an empirical fact in the sense that when you're graphing the exponential function, okay, so this is like x and y, and e to the x will look roughly something like this. So it passes by 1. So what you need to remember is the basic shape. So this will be like e to the x. And then, of course, as well, in this case, it could be u, right? Let's replace x with u so that you can easily relate the graph of the exponential to this particular problem. So because what's happening in this case is that u is approaching negative infinity. So u is actually going this way, right? So, and what you have to look at is the exponential function, and you see that it's approaching 0. So it's really an empirical fact. It's by punching in a couple of values, you see that, yes, the exponential function is approaching 0 when u is approaching negative infinity. All right, so hopefully it helped. So just recapping a little bit, you use this theorem whenever the problem is inside the limit, okay? So it's not the entire limit, it's just like a part of the limit that's causing a problem. So in this case, you do the limit of the inside, that's the thinking process, right? You do the limit of this part, and then you figure out, okay, it's approaching negative infinity. And then the negative infinity becomes what the inside of the exponential is approaching. So that's what you replace your limit by, right? So the inside is approaching negative infinity, and we have just e to the u. And from there, you conclude. Hopefully this was helpful. See you in the next video or in the next class.